This is a math story that I call The True History of Math Induction with Socrates and Amphibianes. The part of Socrates will be played by you, and Amphibianes, oops, wrong frog, will play himself. The True History of Math Induction. Through painstaking research, I have traced the beginnings of math induction to ancient Greece. I have discovered a lost manuscript about the greatest philosopher of all time. Though long since forgotten, at one time he was so great that people called him Socrates. This manuscript describes a dialogue between Socrates and one of his students, Amphibianes, who was always hopping all over him with questions. Throughout the following reconstructed dialogue, notice how Socrates employs the Socratic method, by which the student is brought to knowledge through queries such as, "What's so great about that?" Remember, this is a dialogue. You are playing the part of Socrates, so make sure to come in at the appropriate time.
Oh, great Socrates! I want to possess the secret of the infinite.
To have the secret, Lilyhopper, you must first understand the infinite.
What's to understand? It doesn't take a great leap of faith to see that infinity just goes on and on and on.
So what secret do you seek, O bug-eyed one?
I seek the secret of how you can tell when a conjecture will always work. Let me give you a prime example. Let's take a random expression like n squared minus n plus 41.
What's so great about that?
Well, suppose that you put in counting numbers, like for n, like 1, 2, 3.
What do you get, Tadpole?
Let's see.
Feel free to do this along with us and pause the video. What do you observe, O web-footed one? Take a look at those numbers and see if you notice anything that they have in common.
Well, they're all prime numbers.
All of them?
I don't know.
Will this always yield prime numbers? Pause and decide if that's true. Hint, try 41.
Oh, but an infinite number, I guess.
Any multiple of 41 will fail. Not really a prime example, is it, O pond scum sucker? That's actually a compliment.
Whoops! I guess I didn't work. But if it did, how would I prove that it always worked without trying them all out?
Okay, see those ducks over there? They play a game that they call intense concentration, in which one duck thinks of a set of numbers and the rest try to guess all the numbers in the set. Would you like to play?
Okay, give me a hint. I hate to jump to conclusions. And please, no complex numbers. I have trouble with numbers that have eyes. Stick to counting numbers.
1 is one of the numbers in the set.
Please, please, please give me one more hint.
Okay, if you guess one of the numbers right, I'll guarantee you that the next counting number is also in the set. Does that help?
Let me see.
Okay, think about what set of numbers that may give you. Can you dissect the logic?
Please don't use that word. Okay, it's kind of like dominoes. If you set them up so that if one goes over, the next one always goes over, and you tip over the first one, then they all go over. Wow!
What's so great about that?
Don't you see? This spawns a great technique for analyzing infinite processes. Take a sequence of odd numbers, for instance.
Like your relatives?
No, like odd counting numbers. Say a sub 1 equals 1, a sub 2 equals 3, a sub 3 equals 5. Now suppose that I wanted to find a formula for the nth odd number. What does this have to do with the intense duck concentration game? Well, it looks like a sub n equals 2 times n minus 1. But after the experience with my prime example, I can't trust it unless it can be proved. So I will play the game. A sub 1 equals 2 times 1 minus 1, which is equal to 1. So it works for 1, just like 1 was one of the numbers in the set. Then, if any of them work, and I know that some of them do, let me take the last one I try that works and call it k for Kermit. I know that a sub k is equal to 2 times k minus 1 is the kth odd number. How can I show that a sub k plus 1 is equal to 2 times the quantity k plus 1 minus 1 is always the k plus first odd number?
How, oh fly breath, which is actually a compliment?
Simple. You use the fact that the next odd number is always 2 more than the previous one, so a sub k plus 1 is equal to a sub k plus 2. And substitute the formula that you know now works. A sub k is equal to 2 times k minus 1 to get a sub k plus 1 is equal to the quantity 2k minus 1 plus 2, which is just 2k plus 2 minus 1, or 2 times the quantity k plus 1 minus 1.
What's so great about that?
Well, suppose you wanted to add them all up.
Are you serious?
Sure, the sum of the first odd number is 1. The first two add up to 4, etc. S sub 1 equals 1 is equal to 1. S sub 2 is equal to 1 plus 3, which is 4. S sub 3 is equal to 1 plus 3 plus 5, which is 9.
Is there a pattern, oh tasty legs?
They look like perfect squares to me.
And how would you prove that?
Simple. I'd use the intense duck concentration game again. You see, I've shown that it works for 1. Now I call the largest value that I know that it works for to be k for Kermit. So I now have s sub k is equal to 1 plus 3 plus 5 plus etc. 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 2k minus 1 is equal to k squared. And you see, I had to know a formula for the kth odd number to do this.
Are you finished?
No, I have to show the formula will always work for the next number, k plus 1, if it works for k. In other words, I want s sub k plus 1 is equal to 1 plus 3 plus 5, plus 2 times the quantity k minus plus 1, minus 1 is equal to the quantity k plus 1 squared.
How do you do that?
Simple. I just write the left-hand side with the kth term shown, so I have s sub k equals 1 plus 3 plus 5, 2k minus 1, plus 2 times the quantity k plus 1 minus 1. And then in place of the underlined portion, I substitute k squared because I know this to be true. So I now have k squared plus 2 times the quantity k plus 1 minus 1. With a little bit of algebra, this gives me k squared plus 2k plus 2 minus 1 equals k squared plus 2k plus 1, which is equal to the quantity k plus 1 squared, which is what I was trying to show.
And this helps you understand the infinite?
Sure, I owe it all to you. You introduced me to the intense duck concentration game. I can't wait to tell all the guys back at the plant.
But isn't the name of the technique kind of long?
Yes, you're right. I guess that I should shorten it. How about induction?
And that is how the technique of mathematical induction got its name. Honest.